Hey, this is FixReef, and today we have an unusual device, a controller for Reef Octopus skimmer. This is a fairly simple device. It just controls the motor on the skimmer to spin it faster or slower. It looks like this specific controller is for the Varios 4S, a 24 volt model of the skimmer. And that device is all I got for repair. The issue that it came in with is that it does not ramp up the speed too high. It always stays at low. There is no way for me to test, as I don't have the motor itself to attach to the pump. So we'll have to figure out what's wrong using just the controller. Okay, so before I even do anything with this, again, I'm going to plug it in momentarily into my lab power supply and see if it lights up at all. Okay, so this is a 24 volt model DC, 24 volt DC model. So I'm setting up my lab power supply to 24 volts and maybe about half an amp or about 500 milliamps, so I do not burn anything if there is a problem, if there is a short on the unit. Now let's plug it in and see what we have. All right, hopefully you can see this. It does have a couple of lights come on. Momentarily it had the blue light, the echo mode on, and then it switched to pause. I'm not sure if that's the problem because the pump's not connected. We'll have to find out. Let's see. On again. The eco mode is on. Try to ramp it up. Immediately goes into pause. Let's see what else we can do. FS mode is on and off and seems to be working. If I attempt to ramp it up, it goes into pause. Pause by itself is working. So that's all good. And it just goes back into a problem mode likely because the pump's not connected. So I'm going to be trying to repair this blind, as I don't have a good DC pump to connect to this. Let's see what's inside. So the first question to answer is how to take it apart. This looks like a sealed module. I don't see any screws. So my guess is that it looks like this is potentially where you can open it. Let's see if we can pry it open. Oh yeah, it's moving. It's not as easy as it looks. And it still wouldn't come out because this tab over here, part of the thing that plugs the hole for the connector, but it's off. And we didn't break anything, that's good. Fairly simple and empty inside. Looks like a hobby box type thing with an Arduino inside, but it's obviously not an Arduino. Let's see. I'll need to take the main board off of this. So for this, we're going to disconnect the ribbon cable and let's take some screws out. Looks like I'll need a smaller screwdriver for those two. Okay. Looks like it's sitting in fairly solid, but that's probably because of all of the connectors that are protruding through the box. And of course there is this as well, this board as well for the external connectors. And this wire is soldered. The yellow wire is soldered all the way, so we'll have to remove it at some point. and it's mostly out. Okay, very clean. I don't see any corrosion. I don't see anything bad inside this box. No missing resistors or capacitors that I can see. Now the other side of the board. Of particular interest are those Mosfets here, because on these controllers, these Mosfets are the ones that usually burn out. And they burn out because usually when the pump itself fails, internally, the water gets in, it shorts, it's connected directly to these Mosfets, and so it usually shorts the Mosfets, and they burn out. You may not necessarily visually see it, but that's what typically happens. Oh wow, this is very interesting. I haven't worked on these controllers yet, but by the markings, I'm willing to bet that this is a CAN transceiver, VP230, similar to the ones that are installed on Apex equipment. But it's on the Apex equipment, it's there for a good reason. Here, I have no idea why there would be a CAN transceiver. It looks like it's going into this. So there has to be a communication to through those exposed ports to other equipment. Okay, well, it looks fairly good. Everything visually looks very good. Nothing appears to be missing or burned, has any holes in it, so. All right, now I'm going to look a little bit closer at the controller itself. So this pump wire, as you can see, it's got three wires here, three pins. These are these 3 pins, 1, 2, and 3. These 3 pins are, unlike your typical regular DC motor, this has 3 pins to it because it's a brushless DC motor that's controlled, that can be controlled via this controller using a logic that would allow to manipulate the speed of the pump, the speed of the motor. You can see that there are huge traces going across from here because there is quite a bit of current flowing through this, and so they need to support this. So these 3 traces go over and across, and they arrive over here. And they're connected directly to these MOSFETs. There are 6 MOSFETs. This is a typical configuration for controlling brushless DC motors so that you can have different speeds to them. In this particular case, they're all N-channel MOSFETs. And again, a MOSFET is essentially a glorified transistor that can carry a lot of current through it. So it's an on and off switch that allows the current to flow in a particular direction. And by manipulating these 6 switches, essentially, it spins the motor. So in a particular combination, when some of them are on and some of them are off, it churns the motor a little bit, and then you switch the configuration, it keeps churning, and the faster you switch it, the faster it's going to spin. The slower you switch it, the slower it's going to spin. Once again, as I said, if any of the pins on the, or any of the wires on the brushless DC motor are shorted, that immediately affects the MOSFETs, and they get shorted as well, and they burn out, and they don't work very well. So first, what I'm going to do is I'm going to test just in circuit for any obvious shorts on this MOSFETs. We're not supposed to have complete dead shorts anywhere in here. And it doesn't appear as we have any shorts. What else can be wrong? Alright, so the next thing I'm going to do now that the visual inspection is over and it doesn't look like there is anything wrong, I'm going to try to plug it in again and check to see if anything odd happens, particularly looking for anything that warms up too much. Let's give it some lab power, 24 volts. Obviously there is nothing connected to this controller, so I'm not expecting a lot, but let's see what happens. So first off, this is where the controls and the LEDs are. So once we power it up, it's supposed to light up on us. And it did. Let's see what happens here. So the blue LED that was just here, that was the lowest speed setting. The red LED, I think that means that the float sensor is triggered, but we don't have a float sensor connected anyhow. And now it's blinking red. This is the pause button. That indicates that there is a problem. So it comes on every time it comes on for a brief moment. It stays on for a little while, and then it switches off. Wait a minute. You can't see it on the screen, but on my bench power supply, I see quite a bit of a drop in the current consumption in the amps. Not quite a bit, but it's going from about 40 milliamp. No, it's going from about 50 milliamp down to about 40 milliamp the moment it switches from blue to blinking red. That's quite a bit of a drop for something as small as this controller with absolutely nothing connected to it. How about we do some temperature test on this? I'm gonna plug it in again. Because excessive power consumption usually means that something's getting really hot. I'm not feeling anything. No, not on this end. Alright, let's flip it over. The Mosfets, the bridge is staying nice and cool. The main controller is a tiny bit warm, but it's supposed to be. You can barely feel it's probably just above the ambient temperature here. Oh, wait a minute. What is this? This is fairly hot. Not a whole lot, but hot. I'm gonna plug it in again, give it power. Oh boy. This one heats up quite a bit. Let me zoom in. So this guy over here, heats up quite a bit when I attempt to plug it in. So every time I power cycle with the button underneath, this button, that's the power button for the controller, and it switches the motor, it's supposed to switch the motor on, the pump on, this unit over here heats up tremendously. And the moment it starts timing out, it cools off right away. It's very hot right now, and it's cooling off again. Okay, I'm gonna turn it off. And let's take a closer look at what this is. So this to me looks like some type of voltage regulator. So in this particular voltage regulator, we have 3 pins. This one is ground. This one is V out, and this one is V in. V out for this voltage regulator is supposed to produce 3.3 volts. And V in is the input voltage. Yeah, that's 3.3 volts, as it should. And this is about 11. Okay, so it's producing 3.3 from the 12 volts probably. Okay, so why are we heating up so much? Now um, this voltage regulator that produces 3.3 volts, it serves as power source for a bunch of components on this board. Primarily, it's the main CPU that takes this. I'm sure that the CAN transceiver uses the same. Um, what else? There is no way 3.3 volts are being used by any of the drivers or the MOSFET bridge. That requires a lot more. It requires 24 volts. It requires 12 volts. We're not going to go in there. But the fact of the matter is that this 3.31 heats up significantly when we attempt to turn the controller on, and then it cools off after a few seconds when it times out and the speed light, the blue light, goes off. So what can be causing this trouble? Let's flip the board over and take a look. Obviously, in this state, the controller is the voltage regulator is fairly happy. It's still warm, but it's not anything particularly crazy. The moment we press the button, the power consumption goes up while the light is on, and we have an overheated voltage regulator, and then it comes off. So what I would like to do is, things that I like to do the least is to test these tiny little components that we see over here, because more than likely there is a short somewhere around here. Because again, the tiny components are the components that are going to be using 3.3 volts. These components are not using 24 volts or 12 volts or whatever. These are the 3.3 volt consumers. I bet you that these little LEDs that blink are also 3.3 volts. And this LED is 3.3 volts. So let's take a look under the microscope and see if we find any shorts. Okay, power on. The LED is on. None of the other LEDs are on. Let's test it. Multimeter in continuity mode. I usually don't worry about resistors as they don't get shorted. Okay, the beep. Here is our LED. In fact, this, if we attempt, let me switch the polarity on my multimeter. I bet you that this is, yeah, this LED lights up from just the multimeter. That works. This LED does not light up. I'm guessing it's burned out, but it's not a short. Okay, so far so good. Oh, we have a short on this LED. And it's not on the transistor, on the resistor, it's just the LED. Okay, anything else? All of these LEDs that are supposed to show the status are not lighting up, and one of them is actually causing a short. So what this means, I think, I'm guessing what this means is that whenever the controller turns on, it probably is supposed to light up all of these LEDs in a row. Every time you press this button for speed up, that's supposed to light up the LEDs as well. What's happening is that if one of these LEDs is shorted, that shorts the 3.3 volt power supply or voltage regulator, because essentially a short over here is going to propagate further out into the controller. Okay, now that we know where the problem is, and specifically, likely at least one of the LEDs on this controller is blown, not only blown, but also shorted, causing a havoc out in this circuit, and potentially others burned out, what we need to do is just attempt to replace them. Now, I don't have brand new replacements for these LEDs, which is fine, because I have a donor board from, I think, Gyri controller, which can be used to substitute the LEDs that are being used, because the color is the same blue. So I just need to get these LEDs out and put them back in. Now, to replace this, I cannot use my reflow because the surface is going to warm up quite a bit. and we have other components that I would like to save here. And I cannot use the hot air because hot air is going to just melt these LEDs. So instead, I'm just going to use my soldering iron to remove it. As you can see, with the leaded solder, things just come out much easier. Looks like the heat got the lens off of this, so it's not going to be useful anymore. Let's try this one. That's better. Okay, since we destroyed one of them, next I would like to actually measure the size. I think this is likely 0805 LED size, but we're about to find out. Yeah, this is definitely size 0805 because it's too big for 0603, so 0805 it is. It's way too big for 1206. Okay, now we know in the future which ones to get. Okay, it's time to now start taking the broken LEDs off of the controller in question. Once again, need a little bit of solder. I don't care if I destroy this, it's already shorted. The lens came off. Yeah, I did destroy it after all. All gone. Alright, before I do anything else, just to ensure that this was not a short elsewhere, let's test. And the short is gone. Alright, now that the short is gone, let's see if any of the other LEDs are going to light up. Okay, so this should be the correct. It doesn't. This LED is still not working, just making sure that I got the polarity right. Let's replace one LED that we just took off the board so that the sequence is restored. If there is actually, no, there is probably not a sequence because each individual LED is controlled by the controller. So each of them is powered directly by the microcontroller on the other side. So no, they are independent. So the fact that none of them lighting up may mean one of the two things. Either they're bad, which is more than likely, or there is damage on the main controller. And the main controller is no longer able to provide power to those LEDs. So of course, the worst case scenario for us is that the controller is dead. Okay, just a little bit of cleanup before I start applying fresh solder. Now we're gonna put some fresh solder on there. Let's hope that the other LEDs are not working is just because they're old and they're burned out for the most part. That's good. All right, time to put a new LED on there. Okay, once again, have to worry about polarity. So it's a diode, so the arrow is pointing towards ground, which means that ground is this way. Now I want to be careful with this one. I don't want to mess up the lens, so not a lot of heat, just enough for it to catch it. That's enough. Lots of flux on top that needs to be removed. All right, continue replacing the LEDs. The new LEDs are definitely of a different size, but they seem to work. Okay, over here, this is ground, and this is positive. Flip it around. This is where having hot tweezers would have helped a lot, but okay. And the top one, well, we have it. Okay, I think I replaced all of the LEDs. Now the question is, what's going to happen if I plug it in? Let's find out. And power. Okay, one LED is on. Second on, third on, fourth on, fifth on. All of the LEDs are now on. There's quite a bit of reflection, so it's harder to see. Okay, all of the LEDs are on. And when I attempt to lower the speed, they come off. And then increase the speed, they turn on. All right, so now that we have it done, let's reassemble the board and see what it looks like fully assembled. Power. All of the blue LEDs are on. They're going to time out soon and switch into error because there is no pump connected. Let's turn them on again, and we will just get it down to 1 and back to max. So all of this, let me get it to stay on for a while. All of the LEDs are on now. And the controller is working again. Behind the scenes, so to speak, I also tested the Mosfet bridge as well to make sure that it produces the power that it's supposed to for the pump. So I don't have a pump to connect this to, but I would imagine that it's likely going to now work. So let's review what happened here. There was no other problem on this controller other than blown out LEDs. There are 5 LEDs in this sequence. 4 of them were bad. Of the 4, the third one, the middle one, actually shorted. As you can imagine, LEDs being diodes, they either fail and they just don't conduct, or they short and they conduct permanently through them. When they do conduct, they short things to ground. Because they were shorting things to ground, the 3.3 volt voltage regulator was overheating significantly as it was trying to deal with this. And it would likely get to the point where it just shuts off to prevent more significant damage. Every time that happens, the controller would also shut off, and it will shut off the pump, because there is no direct power connectivity between the power supply and the pump itself. Unlike older controllers where there was just a relay here that would turn it on and off depending on the cycle, this one actually controls the speed, the torque of the pump motor, and without the controller, the pump is not going to work, and that's exactly what was happening here. This goes to show that the LEDs play a significant role in the quality of the controller and the operation of the controller. And it's important to make sure that they're all working properly and behaving properly. But that's all for today. Thanks for watching. If you like this content, please like and subscribe, and I will see you next time.